We live in a digital world where every piece of information is stored electronically, and communication is vital in our everyday lives. To manage such large amounts of data, we use databases to relate information and store it more effectively. One of the most popular ways to store data is relational databases. But who came up with this idea, and what precisely does it consist of? In this video, we will discuss relational algebra, relational calculus, how it is used to create an effective database, and the history behind it.
The relational model was developed in the late 1960s by Edgar Frank Codd, an English computer scientist. Codd studied chemistry and mathematics at Oxford University, but briefly abandoned his academic studies to join the Royal Air Force during World War II. After the war, he moved to New York to work for the International Business Machines Corporation, IBM, as a mathematical programmer, where he stayed until 1984 at the age of 61.
In 1967, while Codd was working for IBM, the company developed the ICS, Information Control System, which was improved until 1969 when it was renamed IMS, Information Management System, and released to the public. This database employed a hierarchical storing method, grouping data into categories.
However, Codd noticed several flaws in the system and worked independently to create his own data management system, which he named the Relational Model. This system can be queried either through the Relational Algebra or through Relational Calculus. Relational Algebra consists of specific operators to compare sets of data. It is said to be imperative. You use algorithms to find an output by dictating to the computer how to get the output and not what to get.
On the other hand, relational calculus uses logical conditions that tuples must satisfy, and it is said to be declarative because we declare conditions that the output must satisfy. Essentially, relational calculus describes what to get instead of how to get it. Codd published his first paper on this topic in 1970, a relational model of data for large shared data banks. Over the next 2 decades, he continued to fine-tune his work and published nearly 30 papers describing in more detail the intricacies of his model. So what is Codd's relational model?
Let's define it together using this data as an example. This is what we'll call a relation. And this is its name. In our relation, we'll call this top row the header. The rest is what we'll call the table of the relation. Each separate element in the header is an attribute. Here they are labeled A1, A2, A3, and this goes on until AN. Attributes are character strings.
In this example, A1 equals ID, A2 equals name, and A3 equals age. We'll define the degree of a relation as its number of attributes. This is the index number n. Here, the relation employees has a degree of 3. Each row in the table will be labeled T1, T2, T3, all the way until Tm. Each of these is called a tuple. They are sets containing the elements of the associated row in the table. Here, these sets are ordered, even though they usually aren't in math. T1 is the set containing the integer 1, the character string Liam, and the integer 25. T2 contains 2, Olivia, and 47, while T3 contains 3, William, and 38.
Next, let's define some domains D1, D2, D3 up to Dn. These domains specify which type of data each column contains. Each element in a column must be in the corresponding domain. In this example, D1 is a set of strictly positive integers, D2 is a set of all character strings denoted S*, and D3 is the set of non-negative integers. Now, we can define a tuple as the set of all elements R1, R2, R3, etc., such that Ri is in Di. A relation just becomes a set of M of these tuples. M is the number of rows of the table and N is the number of columns of the table. Let's also give more information about the relation R by adding D and A in parentheses. Logically, D is the set of all domains and A the set of all attributes. Now, how would we define our employees example relation using this notation?
We can write it as employees with the set of positive integers, the set of all character strings, and the set of non-negative integers as the domains, and the character strings ID, name, and age as the attributes. This definition is equal to the following set, containing all tuples from earlier. Finally, let's also define tuple indexing. T index k, denoted by this bracket notation, is either equal to the value in the tuple t associated with attribute k when k is an attribute name, or it is equal to the value in t associated with attribute ak when k is an integer.
Now, let's define the 9 core relational algebra operations. These by no means make up the full list of relational algebra operations, but they are a solid foundation off of which we can construct complex queries. We will start by defining the first 6 primitive operations. 3 are unary, meaning they only operate on a single relation. The remaining 3 are binary, meaning they operate on 2 relations. The last 3 operations are called the derive operations because they can be defined in terms of the 6 primitive operations.
The projection operation is one of the most important and most common operations in relational algebra. It is written as pi of the relation R on attributes A1, A2, up until AN. The formal definition of the projection of R on A1, A2, etc. is the set which contains every element in every tuple present in R indexed by one of the attributes named in the operation. In plain English, this is the equivalent of selecting one or more columns of a relation by their attributes.
Let's take a look at an example. If we have this relation named employees with attributes ID, name, and age, then the projection of employees on the attribute name is equal to a relation containing only the name column. Similarly, the projection of employees on name and age is equal to a relation containing these 2 columns. The selection or restriction operation, like the projection, is a fundamental component of relational algebra. It can be seen as the complement of the projection, in that it selects rows instead of columns. We write a selection as sigma of R on P, where R is a relation and P is a predicate. A predicate is an expression that evaluates to either true or false, and is made up of attribute names, constants, and a combination of those and of the logical operators and, or, and not, and of the relational operators denoting equality or inequality. An example of a predicate would be ID equals 3. Here, if ID is an attribute name, it is short for T indexed by the ID attribute. Hence, we can define the selection as sigma of R on P is equal to the set of all tuples T such that P. If we substitute ID equals 3 as our predicate, we get the selection of R on the condition that ID equals 3, which corresponds to all tuples T such that T indexed by ID is equal to 3.
Let's look at this example visually to better grasp the concept of the selection operation. Given the same relation employees, the selection of employees on the condition ID equals 3 yields, as anticipated, the row with ID 3, name William, and age 38. This is a fairly simple predicate. Another example of a simple predicate is age greater or equal to 40. This yields 3 rows, which you combine into a new relation. A more complex predicate looks like this: ID not equal to 2 and age greater than 50. Here, rows with ID 1, 3, and 5 satisfy this predicate. They are combined into the relation resulting from the operation. The final unary operation is rename, denoted by row. This operation isn't part of Codd's original paper on relational algebra, so this video won't go into much detail about it. However, it will be useful when defining some derived operations later on. There are 4 ways to use the rename operation. Rename of relation R on R prime simply renames the relation R to R prime. Very complex, I know. Rename of R on a list of attributes A1 through AN renames R's attributes to A1 through AN in order. Adding r prime before the list of attributes renames r to r prime and r's attributes to a1 through an. Finally, rename of r on a prime over a renames r's attributes a to a prime.
The first binary operation is the union, already defined in set theory. The union of R and S is defined as a set of all elements T such that T is in R or T is in S. Relational algebra's union operation differs from traditional set theory, however, because R must be union compatible with S for a union to be possible. Two relations are only union compatible if their degree, attributes, and associated domains are the same.
Let's take a look at an example. Here, the union of E1 and E2 can be performed since E1 and E2 are both relations with the same degree defined on the same attributes and domains. But what happens if we remove the ID column from E2? Now, union between E1 and E2 is impossible because E1 and E2 are not union compatible. Here, one way to make this union operation valid is to replace E1 with the projection of E1 on name and age, effectively removing the ID column. Now the union operation can be performed.
Set difference is another operation defined in set theory. As with the union operation, two relations must be union compatible for the difference operation to be possible in relational algebra. The result, denoted R minus S, is simply the set of all tuples in R not in S. Let's take a look at an example. First, we copy E1. Next, we take every tuple in E2 and match it with an equivalent tuple in E1 if it exists. We finally remove these matching tuples from E1 and are left with the result of E1 minus E2.
The Cartesian product of R and S in set theory is defined as the set of all pairs R and S, where R is in R and S is in S. The Cartesian product of relational algebra is often called cross product to avoid confusion with set theory. R times S in relational algebra equals the set of all sets R1 through Rn and S1 through Sm, where R1 through Rn is a tuple in R and S1 through Sm is a tuple in S. This isn't immediately super intuitive. How can we understand this more easily? Well, let's take a look at it visually. Say I have a relation with many employees, their ID, name, and age, and another relation with last names corresponding to a salary. If I want to find all possible pairs of employees with last names and salaries, I can take the cross product of employees and last names. This will yield a relation with all possible pairs of tuples from the employees and last names relations.
The first derived operation is the intersection, another essential component of set theory. In colloquial language, the intersection of R and S is simply all the tuples both in R and S. For this operation to be valid, R and S must be union compatible. But why? Well, you see, if we take the difference of R and S, we get the tuples in R that aren't in S. Subtracting that from R gives us all tuples both in R and S. The intersection is a derived operation because it can simply be defined in terms of the 6 primitive operations defined before, in this case only the difference operation.
The join operation is similar to the cross product but with extra conditions. The natural join, written R join S, combines tuples from R and S that have equivalent values for their common attributes. The majority of join operations, however, will contain the predicate P. This join operation combines tuples from R and S that make this predicate true when combined. Let's take a look at an example of a natural join first. Here, we have a relation O containing names of people and what kind of pet they own. The relation P associates animal types with a generic name for each. taking the natural join of O and P combines O and P where the pet animal value is the same. Next, let's take a look at an example of a join operation with a predicate. Here, we have some customers with a budget trying to buy houses with a price. Joining C and H where the budget is greater than the price yields a relation where every customer is associated with every house they can afford. Hold on, this is very similar to the cross product, isn't it?
Well, yes it is. In fact, the join operation with a predicate is simply a selection of the cross product R times S on this predicate. The natural join, however, is slightly more complex to derive. If we define A1 through AN to be the common attributes between R and S, then the natural join can be defined as follows. We select on the condition that the value associated with each corresponding attribute of R and S is equal. Sadly, this requires us to introduce additional notation to differentiate R's attributes from S's attributes. But if we don't want to introduce some additional notation, the natural join can still be defined using the 6 primitive operations. Let's label the attributes unique to R, R1 through Rn, those unique to S, S1 through Sm, and those common to R and S, U1 through UK. We get that the natural join of S and R is equal to this expression. What is going on here?
Let me break it down for you. First, we rename every attribute U1 through UK of S to W1 through WK so that they have a different name than those of R. Next, we take the cross product of R and the result of renaming S's attributes. Next, we apply the same selection as before, but now there is no confusion between the attributes. Finally, we project every attribute except W1 through WK to remove the duplicate values.
The last relational algebra operation covered in this video is the division. Let's try to understand it together. If R divided by S equals U, then U times S, or the cross product of U and S, should equal R like in basic arithmetic, right? Well, that doesn't apply when working with relational algebra. If R divided by S equals U, then U times S is merely a subset of R, but isn't necessarily equal to R. Also, in order to be able to divide a relation by another, all attributes of the divisor must also be attributes of the dividend.
Well, this doesn't help us understand division, does it?
No, it doesn't. Let's take a look at a simple example before giving a definition for the division operation. Here we have a relation P and a relation L. Do you notice anything special about these two relations?
Well, yes, I do. P seems to be the result of the cross product of L and another relation.
Great! Well, in this case, P divided by L is exactly this other relation. Let's call it F. Now we can see that P equals L times F, just like in basic arithmetic.
Ah, I see. But what if I remove the last row from P?
Now the result of P divided by F is just Liam and Olivia instead of Liam, Olivia, and William.
But P isn't equal to L times F here.
Correct, and that is why the division isn't exactly the inverse of the cross product in relational algebra. If R divided by S equals U, then U times S is the largest subset of R that is the result of a cross product.
Okay, I think I get it. This operation can be derived from the primitives, correct?
Right, and this is how. Let's use our example from earlier, but let's replace the relation names with R and S. This is how we write R divided by S with relational algebra primitives. Don't worry, it's not as complicated as it seems. Here, A1 through AN are the attributes unique to R. First, we select all the columns unique to R and take the cross product of that and S. This gives us what R could have been if it had been a full cross product. Next, we subtract R to get the rows which would have resulted from a cross product but aren't in R. We project again only the attributes unique to R, giving us, in this case, the first name which has not been associated with all last names. Finally, we subtract this from the projection of R on its unique attribute names again, yielding in this case the first names which are associated with all last names. Notice here that Liam and Olivia are both twice in the result. Duplicates aren't allowed in sets, so we compress the result to only contain Liam and Olivia once.
Hopefully, you start to see the expressive power of relational algebra. Let's look at 3 examples of how combining relational algebra operators can construct complex queries. For our first example, consider a relation called students where student names are each associated with one course they take. Someone might wonder what courses Olivia takes in this context. Obviously, we can tell she takes math, English, and science by looking at the table. But what if we want to query this data using relational algebra?
Well, first we can grab the student's relation. Next, select only the rows where the name is equal to Olivia. Finally, project only the course attribute to remove the names, which we do not require. This yields the result to our question: math, English, and science. For our second example, we have a relation of players in our video game and a relation with items. By looking at this data, a good question to ask is, what items can Percival afford?
To query this using relational algebra, let's first grab the player's relation. Next, select on the row with the player data of Percival. Next, join this with the items relation on the condition that the gold amount is greater than the cost to match many Percival rows with items he can afford. Finally, project only the item column to filter out the unnecessary data. After this, we can see that Percival can afford only the sword and cloak item. For our third and final example, let's not use any example data and define our relations as shown in the relational model. We'll have a student's relation with student names associated with the courses they take. The courses relation describes how many credits each course is worth. The band relation contains student names along with what instruments they play.
Here's a good question we could ask here. Which students who are not in the band take both chemistry and math?
Wow, that's quite a complex question.
It is, but I'll break it down for you. First, we select the chemistry and math courses and project only the course attribute, because we don't care about the amount of credits each course gives. Next, we can divide the student's relation by the result of the previous operations to get the names of the students associated with both chemistry and math courses. Finally, subtracting the names of the students in the band completes our query.
Let's explore Codd's second language, the Relational Calculus. Please note that this section is mostly directly cited from Codd's original work Relational Completeness of Database Sublanguages, whereas the Relational Algebra section was derived from many sources and explained based on our understanding. Let's first define the building blocks of Relational Calculus. We'll keep tuples and tuple indexing from before. A range term is a predicate indicating that a tuple is part of a relation. In this case, Ti is part of Rj. Join terms are a simple predicates with one relational operator between either two index tuples or an index tuple and a constant. Logical operators will help us construct more complex expressions. The quantifiers for all and there exists will be very useful to build queries in the relational calculus.
Next, we'll need to understand the difference between free and bound variables. Free variables are not bound by a quantifier. Bound variables are bound by a quantifier, either for all or there exists. For example, in this expression, t1 is a free variable and t2 is bound by the there exists quantifier. The well-formed formula, or WFF, is a core component of relational calculus. It is defined as follows. 1. Any term, either a joint or range term, is a well-formed formula. 2. If gamma is a well-formed formula, so is not gamma. 3. If gamma 1 and gamma 2 are well-formed formulae, so are gamma 1 and gamma 2, and gamma 1 or gamma 2. 4. If gamma is a well-formed formula in which t occurs as a free variable, then for all t of gamma and there exists t of gamma are well-formed formulas. 5. No other formulae are well-formed formulae. In plain English, a well-formed formula is simply a predicate combining range and joint terms with logical operators according to some rules.
Let's also define some special types of WFFs. A range WFF is a WFF containing only range terms and no quantifiers. A range WFF over T is a range WFF with only T as a free variable. A proper range WFF over T is a range WFF over T where the not operator always follows the and operator and where T's range terms all use relations that are union compatible with one another.
Now, a range-separable well-formed formula is a well-formed formula that has the form U1 and U2 and etc. up to UN and V, and follows these constraints. First, n is greater or equal to 1. Second, UI is a proper range well-formed formula over Ti for I equal to 1, 2, up to n. 3. V is either null or it is a well-formed formula with these properties. A. Every free variable in V has a range specified by one of U1, U2, up to UN. B. Every quantifier in V is range coupled. What that means is we replace for all t of delta with for all gamma of delta, which is equal to for all t of not gamma or delta. We also replace there exists t of delta with there exists gamma of delta, which is equal to there exists t of gamma and delta. This is to introduce the proper range well-formed formula over t gamma into an expression where delta is a well-formed formula with t as a free variable but no range terms. In colloquial language, range coupled simply means that every variable bound by a quantifier must have a range associated to it right next to the quantifier. And finally, C. V has no range terms except those associated with a quantifier as in B.
A query of the relational calculus is called an alpha expression, denoted as a set of elements T such that W. Here, T is a list, called a target list, consisting of the tuples or index tuples T1 through Tk that indicate where our answer is. W is simply a range-separable WFF. Here, every tuple variable in T must be a free variable of W. One way I like to think of this is that every UI in W sets the range of a free variable, and V is the expression describing what a query must satisfy. As an example, consider the relations players and items from our second example in the Relational Algebra section. Here, we have renamed the player's relation to R1 and the item's relation to R2. Let's answer the same question from before, but using relational calculus. What items can Percival afford? We can answer this question with the following alpha expression. Z is equal to the set of all tuples T1 indexed by 1 such that T1 is in R2 and there exists a tuple T2 in R1 and both these tuples satisfy that T2 indexed by 1 is equal to Percival and that T2 indexed by 3 is greater or equal than T1 indexed by 2. Pretty neat, isn't it? We have a query expressed in two separate languages. In this expression, T is equal to the list containing T1 indexed by 1, U1 is equal to the range term R2 of T1, and V is the expression describing our conditions.
Before we move on, let's quickly give some additional ways of using relational algebra. If we write a projection or a selection operation containing attributes A1, A2, etc., this means that AI is the attribute in position I of relation R. Also, a projection on a set C, where C is a set of strictly positive integers, is a projection on every attribute that has its position in the set C. For example, if C contains 1 and 3, we project on the first and third attributes.
Now, we will take a look at the reduction algorithm to convert a relational calculus query to an equivalent relational algebra expression. How can we go from our expression z to a query seen in example 2? Let's find out. Let's first let n be the number of free variables in W and b the number of bound variables. Recall what our expression for v is. For step 1, we'll first convert v to pre-next normal form. This means that every quantifier in v must be put at the start of the expression, and that becomes the prefix. The heart of the expression without quantifiers is called the matrix. In our case, the expression v is already in pre-next normal form. Next, we'll convert v's matrix to disjunctive normal form. This means that we use the OR operator to combine terms using the AND operator. In our expression, we have no OR operators, so it is already in disjunctive normal form. Next, we'll remove all the logical NOT operators by converting their associated relational operator theta to its complement. The complement of the equals operator is not equals. The complement of greater than is less than or equals, and so on. Finally, we'll rename all the tuple variables in Z to T1, T2, up to Tn plus b in order of appearance. Now, for each bound variable Tj in V, j equals n plus 1, n plus 2 up to n plus b, we define the following. Let Tj's quantifier be Qj, and let Uj be the proper range WFF over Tj.
For step 2, let's convert the ranges from relational calculus to relational algebra. For each tuple variable in W, we'll define Sj to be Tj's range. This is how we obtain Sj from Uj. For range terms, we just remove the parentheses. We replace the OR operator with the union operation. When a conjunction is followed by a negation, we replace both with a difference operation. A conjunction alone becomes an intersection. In our case, we just have a single range term for each of our tuples. T1's range is R2 and T2's range is R1.
Now, on to step 3. We'll define S as a product of n plus b relations x1 through x n plus b. Xj is equal to Sj unless Tj is bound by a universal quantifier, the for all symbol. In that case, Xj is equal to h of Sj, which denotes the union of all relations union compatible with one of the relations used to derive Sj in step 2. In our case, no tuple variable is bound by the universal quantifier, so we have S equal to the cross product of S1 and S2. Now, if we let Dj be the degree of relation Xj for j equals 1, 2, up to n plus b, we can define μj as the sum of all degrees before relation j. This is super useful to select the correct attributes in the cross product. In our case, μ1 is equal to 0 and μ2 is equal to 2.
In step 4, we'll remove the quantifiers and their associated ranges from V, keeping only the matrix. Now, we'll define T n plus b to be equal to S if V is null. Otherwise, we define it by rewriting V's matrix according to these rules. The logical OR becomes a union, and the logical AND becomes an intersection. These two expressions describe how to rewrite equalities or inequalities with index tuple variables and constants. They become selection operations of the relational algebra. We recommend pausing the video to take a look at these rewriting rules to understand them better. In our case, we rewrite V's matrix like so, and n plus b equals 2.
We're almost there. Now, for every bound variable Tj in V, starting with the last one and working backwards, we'll define Tj minus 1 as follows based on the tuple variable's quantifier. Tj minus 1 is equal to the projection of Tj on Cj if Qj is the existential quantifier. Otherwise, Tj minus 1 is equal to the projection of Tj on Cj plus 1 divided by Sj if Qj is the universal quantifier. This is how Cj is defined. In our example, n plus b equals n plus 1 equals 2, so we have j only equal to 2. Q2 is the existential quantifier, so we have T1 equal to the projection of T2 on C2. Here, C2 is the set containing 1 and 2, so we have T1 equal to the projection of T2 on its first and second attributes.
Now, on to step 6. Recall that T is formed of k tuple variables, indexed or not. We'll identify each tuple variable in T by RH for h equals 1, 2, up to k. Next, we'll define CH for each RH in order to either project an entire tuple or only the specified attribute if it's indexed. Finally, we'll define T to be our final query expression by projecting Tn on the union of k of these sets. In our case, we only have one tuple variable in our target list, so we have R1 equal to T1 indexed by 1. Now, our only C set, C1, contains 1 plus mu1, which is just 1. Hence, our final expression T is the projection of T1 on its first attribute.
And that's it. The reduction algorithm is basically complete. For step 7, we'll substitute the variables from our previous expressions to get a relational algebra query using the original relations. Taking our final expression, substitute T1, substitute T2, substitute S, and finally substitute R2 and R1. This is our final relational algebra expression. But now, how is this expression equivalent to the one shown in example 2 of our relational algebra section?
Well, let me show you. First, notice how our two projections are redundant, because the outside pi is projecting a subset of the inside pi. The inside projection can be removed without altering the result. Next, notice how we are taking the intersection of two selections on the same relation, the cross product of R1 and R2. We'll combine these two selections by replacing the intersection with a logical AND operator inside our predicate. Now, let's replace the positional attributes with their names instead. Here are the attributes of R2 times R1. We can see that the first attribute is item, the third is name, the fifth is gold, and the second is price. Let's substitute these into our expression. Now, let's turn our attention to the other expression. Recall that a join operation with a predicate is simply a selection of a cross product. Using this identity, rewrite the join operation in the expression. As we did with the intersection before, we can combine two selections which are applied one after the other by taking a conjunction of their respective predicates.
And there we go. We have two equivalent relational algebra expressions, almost identical except for the order of the relations in the cross product. It doesn't change anything in the result, however, so they are indeed equivalent. We defined two separate query languages, one imperative and the other declarative, and showed how to convert from the declarative language to the imperative one. I think that is pretty neat. If the relational calculus and the reduction algorithm seem overly complicated, don't worry, it was for us too at first. We recommend creating your own relational calculus queries and going back in the video with a pen and paper to work out the equivalent relational algebra expression. You will definitely get a better grasp of the algorithm this way. In Codd's paper Relational Completeness of Database Sublanguages, he affirms that while relational algebra is free of quantifiers, relational calculus is superior because its logical constraints are more effective and flexible than the algebraic algorithms, thus optimizing the process. Now that we've seen how the relational model works, let's find out what happened next. At first, IBM did not want to implement Codd's model as it will lose revenue from the IMS. However, Codd showed IBM's clients his model's potential, and they in turn pressured IBM to abandon the IMS and establish a new system using the relational model. Thus, IBM put Donald Chamberlain and Raymond Boyce in charge of developing such a system, which they named SQL, short for Structured Query Language.
However, SQL did not adhere entirely to the relational model, which did not go unnoticed by Codd. These new relational databases such as SQL were very popular because of their flexibility, efficiency, and reliability, and several companies were quick to incorporate them. However, they deviated from Codd's original principles of a relational model. Thus, in the 1980s, he published several papers on missing information in database management systems and the fatal flaws of SQL. He even published a set of 13 rules, ironically known as Codd's 12 rules because they are numbered 0 through 12. They are a set of constraints to determine if a database management system is really a true relational database. While Codd is overshadowed by SQL's popularity nowadays, he was a very prominent programmer in the pre-internet computing era. He even won the Turing Award in 1981, considered one of the most prestigious computer science prizes.
Data management systems are essential for any kind of data storage in almost all fields. Nowadays, relational databases such as MySQL and Postgres are compatible with most programming languages. Also, raw SQL queries have fallen out of favor, often replaced by ORMs because they are more intuitive to work with. On a final note, many other types of databases have emerged since the glory days of IBM for various applications. Some examples are key value, graph, document, and most recently, vector databases.
We hope you learned a bit about how Codd's relational model works and its significant impact on data management systems. Also, if you want to experiment with relational algebra and its relationship to SQL, we leave you with the Relax and Relational Playground websites, which are great tools to help familiarize yourself with relational algebra and its operations and were used in the making of this video.
Relax is the Relational Algebra calculator with a lot of functionality, and the Relational Playground allows you to enter an SQL query and see what the equivalent Relational Algebra query is.
Thanks for watching!